This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning, everyone. I just want to warn you, I'm a bit distracted. Just like 10-15 minutes ago, I found out that a female academic from Melbourne Uni was killed just yesterday by a falling tree in Princess Park. So I'm just sort of, I know the name, I know the person like by sort of name, but yeah, it's just it distracted me, so I'm a bit sort of, bear with me through this lecture, okay? Okay, so today we will cover Laplace transform. This is a tool that you should have seen already because prerequisite for this subject is signals and systems, and in that subject you should have covered this in detail. Now, this lecture is a brief overview of the material that I find most sort of important for this subject. At the end of the slides of this lecture, you will find some of the proofs which I think are useful to you. We won't work through them in the lecture, but I urge you to go through them on your own. Okay? So we will concentrate during this lecture on how to use Laplace transform to solve certain problems. Okay? And through tutorial questions and also through your labs, you will use this more. And think of this as one of the most important tools for analysis and design that you will learn in this subject. So it's a prerequisite. Now, if you are struggling with any Laplace transform questions, please, this is the time to go and revise them because you will struggle for anything that comes later if you don't do that. All right? So this is a very brief lecture, but a very important one. It's just a reminder that you need to know this material. Right? We will spend a little bit of time sort of helping you sort of recall some of the important issues. All right, so I'll first motivate this material a bit. Then I will first talk about complex numbers. These are very basic facts, but I think it's important to just refresh your mind. How to add two complex numbers, multiply two complex numbers, how to represent complex numbers in complex plane. That's very important. You will see later on that when we look at, for instance, root locus, complex plane would be like a design tool. So we will be placing the poles of the closed loop system in certain regions of complex plane because we hope to achieve certain performance specifications. So complex plane is a very important sort of tool in analysis and design of control systems. We will introduce definition of Laplace and inverse Laplace transforms, and then I will present a table of Laplace transforms, and we will sort of recall some of the main properties and some of the main Laplace transforms of typical signals like step signal, impulse signal, etc. And then we will look at partial fraction expansion. It's a very important tool. You will inevitably need to use this tool in pretty much any question you would attempt. So partial fraction expansion would be all over the place. That's why we will spend a bit more time talking about that. And I will be presenting different examples throughout the lecture. Just remember, so you can remember how to use Laplace transform in solving different problems. And then we will just wrap up with conclusions. All right. So why do we do Laplace transform? Why do we learn about it? Well, it really simplifies analysis and design of control systems. I mean, in signals and systems, you may have used Laplace transform more for analysis. In this subject, you would use it for design. All right. So we will sort of go next step, in the use of Laplace transform. Why is it useful? Well, instead of manipulating orderly differential equations in time domain, you can actually solve ODEs, orderly differential equations, with algebraic operations, addition, multiplication, division, things like that. So it simplifies things immensely if we use Laplace transforms. Also, you will see that, and you may have seen it already in signal systems, it leads to important concepts such as zeros of a transfer function, poles of a transfer function, and these are concepts that will be used for design and analysis. Later on, when we talk about stability, for instance, of a closed loop system, you will see that it's related to the location of poles in the complex plane, right? So it leads to very, very important concepts. And then, algebra of block diagrams is an important design tool. So Laplace transform leads to block diagrams, right? And then algebra simplifications of these block diagrams become a very important tool in control engineers' toolbox. So, all right, so that's all motivation. So it's an important topic. And I urge you to revise it, go back to signal systems material, revise it thoroughly, because we will use it over and over again, right? All right, so first let's just remind ourselves what complex numbers are. Well, if they are numbers that consist of like two parts, you can think of them as numbers that have a real part and imaginary part. This j here is a square root of -1. It's just an imaginary number. And we can represent these complex numbers in different ways using Euclidean coordinates, which is really real plus imaginary. So real and imaginary parts can be represented as coordinates in a complex plane, right? So we can represent complex numbers as points in complex plane. But we can also represent these complex numbers in polar coordinates, where the distance of the number from the origin is the magnitude of the number, and then the phase is given by the angle that this line connecting the number to the origin and the real positive axis make, right? So we can write it as the magnitude times exponential j times phase. I use this sort of angle, sort of z, as a for phase, to denote phase, and just absolute value is its magnitude. Right, so this is not absolute value of a real number. This is a complex number, so absolute value is basically square root of real part squared plus imaginary part squared. All right, so this is just to remind ourselves what complex numbers are. Note that in this part, we have that the real part of a complex number is positive. And in this half plane, we have that the real part is negative. We will see that this negative half plane is very important. Do you remember why? Stability. So you will see when we represent our model with a transfer function, then all poles of the transfer function needs to be strictly in the left half plane in order for the system to be stable. We will talk about that in more detail later. All right. So here is one just example with lots of different, so red dots represent different complex numbers, and they are presented here in polar coordinates. For instance, this number only has a real part, it has magnitude 1, it's on the unit circle. So this circle here represents the unit circle. By the way, if you go to, let's say, Z transform, then unit circle becomes also important. If you go to advanced control, we would use both Z and Laplace transforms for analysis. In this subject, it's just Laplace. But anyway, so this number has only a real part, which is basically 1. There's no imaginary part, and it can be represented as exponential g 0, where phase is 0, right? So each of the red dots you can go on your own and sort of relate, the representation of these complex numbers to their location in the complex plane. Right? So we don't have to go through all of them. Please do this on your own. So for instance, this one has, so this is a minus j, so in Euclidean coordinates, representation of this complex number is just minus j. Real part is 0 and imaginary part is minus j, but that can be also represented as e to minus j pi half. So minus pi half is the phase, because so positive phase is measured in counterclockwise direction, and negative phase in the clockwise direction. You can go through each of these red dots and sort of figure out related to the mathematical representation, and I urge you to do that. How do we add and subtract complex numbers? Well, addition is best done using Euclidean coordinates. I mean, you can always do addition and multiplication, any operation, either in polar or in Euclidean. But I wrote here addition in Euclidean because it's easier. So how do we add two numbers? Well, we add their real parts and we add their imaginary parts. Right. So that's how we do addition. Here, multiplication is presented in polar coordinates because it's simpler to represent in polar coordinates. So the magnitude of the product would be product of the magnitudes of the two numbers, and the phase of the product will be the sum of the phases. It's just simple. You can do multiplication in Euclidean coordinates. So what would be the real part of the multiplication of two numbers in Euclidean coordinates? Can anyone tell me? If I multiply R1 plus JR1 times R2 plus JR2, what would be the real part of the product in Euclidean coordinates? Yeah, so R1 times R2 minus I1 I2. You can do that, right? So, but it's easier to do it in this in polar coordinates. Thank you very much. So exponential of a complex number is given here. By the way, here I use the Euler representation, of the EJI, so I can represent it. This is just Euler formula, because exponential to j, I is cosine I plus j sine I. You can go to the unit circle to sort of verify this formula. In this picture, for instance, if you consider a number like this, on the unit circle, you can quickly get our formula from trigonometric identities, right? Okay, so now that we introduced complex numbers and some basic operations on them, we can introduce Laplace transform. Before we do that, I just want to remind you how we would use Laplace transform. So typically you would start, and by the way, you can come back to this slide once we've covered more material. It would make sense what we are doing if you go back to this slide, but it's useful to mention it here. So once we cover more material, please revise it, but this will make much more sense once we've done stability, analysis, design, etc. So what do we normally do? Well, we would do modeling using maybe first principles in time domain. Typically, you have an ordinary differential equation, right? Then, in time domain, you may also specify performance requirements. If you remember, when we talked about transients, we talked about undershoot, overshoot, rise time, settling time as characteristics, features of the step response. You might be given specifications in time domain. Right? So then what you can do is you can go in step 3 basically translate all of this like model and specifications into the complex or Laplace domain. This is very easy. I'll just put it here. There's a draft. Okay. So why do we do this? Well, it turns out that the design and analysis can be much more easily done in complex plane. So I can, for instance, for second order systems, I can translate the requirement on overshoot into locations of the closed loop or closed loop poles in the complex plane. And then if I can design controllers so that the closed loop poles are in that region, then I satisfy the requirement. So we will see when we do root locus that we can systematically design controllers to achieve this movement of poles by design of controllers. So design and analysis are much easier in complex plane. So we took our Laplace transform, we then analyze, design things in Laplace domain, and then we take inverse Laplace transform to basically interpret our results, verify, simulate. You would typically simulate in time domain, etc., etc. But this sort of, it may seem like a lot of work to first take Laplace transform, do the analysis, design, and then go back to the inverse Laplace transform. But trust me, this simplifies the design and analysis immensely. That's why we do it. Are there any questions here? No? All right. So this all set the stage for the definition. So look, I just remind you the mathematical definitions of Laplace transform are given here. So Laplace transform of a time signal, think of y of t as a time varying function, right? When I take Laplace transform of that time varying function, I would get something that depends on some complex number s. This s is a complex variable number. Think about it. It's a number. And how we convert this time varying signal into a complex like Laplace transform using this integral. So note, it's a definite integral. We integrate from 0 to infinity, and we have here minus exponential st times the signal and dt. So note that we are integrating over t. So when we take this like integrate from this bound to that bound, time dependence is lost. The only dependence left is on s. Right. Here is a function, so this should have been capital Y. Typically I use capitals for Laplace transform, so this should have been, this is a typo. I like to use capital letters for Laplace transforms. So inverse Laplace transforms of Y of S is some time varying signal, right? Signal that depends on time. And this is the equation that you can use to go back to time domain. One important point is that Laplace transform is well defined only on the region of convergence, so-called region of convergence. So if you are given a signal y of t, and if the signal satisfies this inequality, by the way, this sigma can be positive, right? Then the region of convergence is all sort of s's, where with real part of s greater than or equal to sigma, where sigma is just some real number, and k is just something that's smaller than infinity. All right, so all of this is maths, and that's why often students say, well, this subject is very mathematical, and it's just maths. It's not just maths. This is just a tool, right? So we want to use this tool now for analysis and design, and we will see through many examples how to do that. Now, when you are given a problem, you will not calculate Laplace transform, inverse Laplace transform using the definitions that's given here. Typically, you are given tables of Laplace transforms. So, you know, your exam would be open book exam, and you will have textbooks, you know, available to you. Each of those textbooks would contain Laplace transform tables. Some of the books have more comprehensive tables than others. So some books contain more signals directly in the tables than others. But no matter which book you use, if you know partial fraction expansions, and if you have those tables, you will be good. So There's no problem. Any book would do, really. So what do we find in these tables? Well, in the first column you have these signals that are functions of time. Then you have their Laplace transforms, and then you have their regions of convergence, right? So only for sort of these regions of convergence are these Laplace transforms well defined. This table is taken from Goodwin, Grebe, and Salgado, but Ogata, Franklin, and Powell at the back of the books have comprehensive tables of Laplace transforms also. You can use those books as well. So let's just look at the first row. So that function there, which basically says it's 1, right? So this means that f of t is 1 for positive time, so and it's 0 for negative time. All signals are defined to be 0 for negative times. So the first row basically defines a step function, which is 0 for negative time, and then it's 1 for positive time. So unit step function. So what does Laplace transform table tell us? Well, the Laplace transform of this unit step is 1 over s. And you probably have seen this in signals and systems. The second row is Dirac function, impulse function. So this function has infinitely short duration and infinitely sort of large amplitude, but the area formed by this rectangle is 1, right? So the duration is epsilon, and the amplitude is 1 over epsilon. So that's the Dirac function. So the Laplace transform of the Dirac function is 1. What's that function? It's like you're applying like impact force of infinitely high magnitude to your system, for instance. So this can measure sort of also model impacts, right? Etc. So you have here, so this is called the ramp, just a t, right? The function that's 0 for negative time, and then just it's t, it grows gradually. That's called the ramp. So its Laplace transform is 1 over s squared. I don't talk about regions of convergence here, but they are listed there, and their interpretation is given in the previous slide. So all of these are important. Laplace transform of exponential, cosine, sine, you know, these are typical things that you would encounter in many different questions that you will deal with this subject. In this next slide, we have properties of Laplace transforms listed. So these are basically just properties that you can use in solving problems. The first property says that the Laplace transform of a weighted sum of I functions fi is basically the weighted sum of their individual Laplace transforms. So this is the linearity of Laplace transform. So the second row is very important, derivative row is very important. So Laplace transform of a derivative of a function is s times the Laplace transform of the function itself minus the initial condition. So the second row, very important, very important. We will use this when we calculate transfer functions by setting initial conditions to 0, for instance. Integral, you have, if you take a Laplace transform of an integral, then it's 1 over s times the Laplace transform of the function itself. Delay is given here, so basically if you have a Laplace transform of a function which is delayed, this thing here, mu times mu of t minus tau, is like a unit step shifted by tau seconds. So it's 0 for all times smaller than tau, and it's 1 for positive time, larger than tau. So that's exponential of minus s tau times the Laplace transform of the signal itself. This is also, the last three rows are very important. So Laplace transform of the convolution is the product of Laplace transforms of the signals f1 and f2. If you remember, we already presented convolution in one of the previous lectures. So we said that the output of an arbitrary linear system can be represented as a convolution of the impulse response and the input. So basically, if we apply to that model of linear systems this formula, you would see that the Laplace transform of any output, right, is equal to Laplace transform of impulse response, product of Laplace transform of impulse response and Laplace transform of the input. So this would lead to the important concept of transfer function. Okay. And also final value theorem, initial value theorem, if you want to find the limit of this function y of t in time domain as time goes to infinity, this is the same as finding a limit as s goes to 0 of s times y of s in complex domain. But in order to apply final value theorem, you have to have that this limit exists. And this limit would exist only if you have appropriate stability properties of this, y of s. So we will talk about that later. But note that final value theorem can only be used under certain conditions. You first need to check those conditions and then apply the final value theorem. If you apply final value theorem without checking those conditions, you may get the wrong result. So you might find that this limit exists, but if you actually find the limit in time domain, it might oscillate or grow unbounded, although limit here exists. So you may get the wrong answer. Right? We will, remind you of that. I'll remind you of that when we start using final value theorem more. All right. So look, this is all supposed to be familiar territory. It's supposed to be. If it's not, if you forgot, please revise it. So I want to now go more sort of in applying these things on several examples. But before we do that, I just want to emphasize, I included some of the proofs of some of these properties of Laplace transforms at the end of the slides. Please go through them. It will help you understand the theory much better. But I won't go through that in this section. So it is essential that you know how to use Laplace transform in solving problems. This is, essential for this subject. I cannot emphasize it enough. Right? Let's look at an example. So now we want to just see how things work in an example. So what I want to do is, I want to consider a differential equation that looks like this. This y can be temperature in this room, and u might be basically the desired temperature that I set on the wall. So that might represent a closed loop system where the input is the desired temperature and the output is the true temperature, perhaps. Right? But here we are given a model in time domain, and we are given initial conditions. So maybe there is an initial temperature in the room is 10 degrees, for instance, and we want to find how would temperature change if we assume that u changes as a unit step. So we gave the desired temperature to be unit step. It went from 0 to 1, and then initial temperature was 10, that's the initial condition, and we want to find how true temperature changes over time, how y changes given this input and given this initial condition. So what we do is we just we take Laplace transform. How do we solve the problem? We take Laplace transform of both sides, right? Laplace transform of this derivative is basically this. That's exactly what the tables of Laplace transform told us, right? If you go back to the tables, second row, Laplace transform of the derivative of a function y is s times y of s, which is Laplace transform of y, right? Minus the initial condition. That's exactly what this is. Laplace transform of this guy is y. Now, what I also used here, I took Laplace transform of y dot plus y, but that's the same as Laplace transform of y dot plus Laplace transform of y. I use linearity of Laplace transforms at this step. So this is simple, so I just replace, this by y of s. And why do I have here 1 over s? Well, that's the Laplace transform of the step. That was the first row. So I just remind you, that's the first row in this table. That's how you use. So you get your problem, you from the description of the problem, you will need to plug in what the inputs are, what the initial conditions are, and off you go, right? So what we get at the end is this, right? Where y at 0 is given to you to be 10, right? So now what we do is we solve for y of s. By the way, now the only thing that we don't know is y of s. So this was just an algebraic equation. I can solve for y of s. Y of s appears here and here. I take y of 0 on the other side. I have s plus 1 multiplying y of s. I will divide everything by s plus 1, right? And that's what you get over there. The first part is due to the initial condition, the first term, and the second term is due to the input, right? Now we need to apply basically inverse Laplace transforms to find y of t. That was the question. We were supposed to find y of t. But if you now look back at the Laplace transform tables, the second term, that guy, you cannot find in the tables I gave you. If you go back to this table here, you cannot find in this table 1 over s times s plus 1. You can't find it. So what you do then, you need to express that as a sum of two things that you can find in the tables. That's called partial fraction expansion. So what we can do is we can represent this guy, and at this stage, just trust me that it's true. We will present the general formula in a moment. At this stage, just trust me, you can represent this guy as a sum of 1 over s minus 1 over s plus 1. Now, good thing about this is, well, 1 over s plus 1 and this 10 over s plus 1 can be simplified to do this, and we have left here with 1 over s. These two guys can be found in Laplace transform tables. So then we use inverse Laplace transform, and we find that y of t is inverse Laplace transform of that plus inverse Laplace transform of that. I'm using linearity of Laplace transform again. And that's basically non-exponential to minus t plus 1. Everything is multiplied by a step function. So all of these functions are negative, 0 for negative time, and they are whatever is given here for positive time. So look, what is important to note here is that solution of an ODE, ordinary differential equation, particular solution, was obtained by just using algebraic manipulations and use of Laplace transforms, like just going one direction and the other direction. That simplifies analysis and design a lot. If I gave you a very large ordinary differential equation with initial conditions and its inputs and told you solve it in time domain, you can, but it's much harder. So we want to simplify our life, and that's why we do it this way. Are there any questions at this stage? All right. So now, if you are perhaps asked to calculate limit as t goes to infinity, then one way to do it is you already obtained y of t using inverse Laplace transform. We got it. So we can always use a limit on the time signal that we obtained, and that's always true. So that step, you just need to use mathematics on limits of time sort of varying functions, right? But if you want to, so obviously this in this case exponential to minus t will go to 0. So obviously this will just tend to 1. Right? What's interesting in this case, if I interpreted input to be desired value of the temperature, and if I interpreted y of t to be the true value of the temperature in the room, then the step input, which is desired temperature going to 1, would result in true temperature converging to 1. Right? So that's a cool thing, so it's a cool interpretation, right? So, but let's go back to this just mathematically. So we obtained y of t before, so we can just plug it into this equation and use the limits, whatever you know, on limits of functions, and write this result. However, you do not need to find y of t to find this limit. You can use the final limit theorem and do the limit in Laplace domain. So that simplifies things in many cases, but you have to be careful because you need to satisfy certain conditions. So we can use final value theorem by saying, well, this will be equal to this, but this is equal to this only if limits exist. In this case, we already checked that the limit exists in time domain, right? But later on, we will learn how to check this without going to time domain, using poles, etc., of the complex function. So if you check here, limit as s goes to 0, and s times this is again 1. Right. How you can see this? Well, this term will go to 0 as s goes to 0, and this term would go to 1, right? But you need to always check that limits exist. So do not blindly apply final value theorem before checking things. This is homework. I won't dwell on this. I just want to move on because we have more material to cover. All right. So in the example, one step that I skipped quickly over was transforming this term, 1 over s times s plus 1, into two terms, sum of two terms. Why is this important? Well, you will never find a book that contains all possible terms that you can find when solving these problems. You will always have some basic terms. But what's interesting is you can represent any arbitrary Laplace transform of a signal into a sum of things that you can find in books. And that's called partial fraction expansion. So because it's so important, we want to present now formulas for partial fraction expansion in general. So we want to look into this step more carefully and give a general formula for it. Okay. So what is partial fractional expansion? So if I'm given, an arbitrary function, so what is given here is basically a rational function of s, and if you get that as your solution in your problem, you get that the g of s is a Laplace transform of the signal you are interested in. You will need to find the inverse Laplace transform, but this thing can be very, very complicated. This can have in both numerator and denominator polynomials of very high order that you will not be able to find a book that contains all possibilities. So what you need to do is you need to rewrite this rational function as a sum of very simple rational functions that look like this. Right. So that's what you need to do. So in order to go from this step, which is sort of the initial step, to something like this, that's called partial fraction expansion, it's useful to look at rewriting these polynomials here in numerator and denominator in this form. So I have here this pi symbol means product. It's like similar to sum. Sigma is like sum, this pi is like a product. And I take this product from k1 to n, and this product is from k1 to n. These beta i's and alpha i's have special meaning. Do you remember what they are called? Like if g, for instance, was a transfer function, what would these things be called? Poles and zeros. If g was a transfer function, right, they would be called poles and zeros. So we'll come to that later. So what are these beta k's? They are zeros of this polynomial. When I set this polynomial equal to 0, find all its solutions, that's beta k's. If I set this polynomial here equal to 0, right, and find alpha k's, that's basically where they come from, right? So alpha k's and beta k's are zeros of these two polynomials in that rational function. So now the claim is that if all of these alpha k's are distinct, then the formula for partial fraction expansion is given here. So first you have to find poles. If poles alpha k's are distinct, then you can write this thing as a sum of things like this, where b k's you can find using this formula. So what is this formula? You multiply your original function g by s minus alpha k. By the way, bk corresponds to delta alpha k. No, bk and alpha k go hand in hand, right? And then you can rewrite the original rational function as a sum of simpler rational functions. The bk's here are called residuals, right? And they may be in general complex numbers. And alpha k's, beta k's, and bk's can all be complex numbers. So obviously, if we now represented first g as a sum of these guys, then obviously the inverse Laplace transform of g, which is g of t, is a sum of terms like this. But note that all of these guys can be, as I said, complex conjugate. Complex numbers. bk, alpha k can be complex numbers. So this is a formula. So if I give you an arbitrary function, you can find its poles first, and then plug in those poles into this formula, you compute bk's, and you rewrite everything in this form. This can be always found in tables of Laplace transform. You can even memorize it, right? It's very easy. So if we consider that example, so in that example we considered before, there was this term here. So I want to just apply this formula to this term to demonstrate that indeed what I wrote before is correct, right? So we have the poles here are s equals 0 and s equal minus 1. They are the values of s for which the denominator vanishes. They are the poles for this guy. So now I have to use, so to calculate b1, I multiply by s minus 0, right, which is s. That's the first pole, times g of s. Well, you can find that, you get 1. And similarly, if I multiply by s plus 1, so by the way, this s and that s will cancel, and then since s goes to 0, you will just have, this whole thing is 1 over s plus 1. As s goes to 0, you just get 1. It's clear. It's clear from the expression for g. Similarly, b2 you get is just 1 over minus 1. And we confirms what we showed before. We showed before that this function there can be represented as 1 over s minus 1 over s plus 1. That's exactly what we got from the calculations there. So just a note, we won't go through all these steps, but I just want to explain what's given here. I told you that bk's and alpha k's can be complex numbers, but from the theorem of algebra, polynomials with real coefficients, if they have zeros that are complex, then they will always appear in complex conjugate pairs. So because I know that I will always have complex conjugate pairs, I know that I would always, if bk and alpha k are complex numbers, then there will always be another term where bk star, which is complex conjugate, and alpha k star is a complex conjugate of alpha k. They would appear in pairs. So if you now, look at, alpha k and bk represented in this way, you can see that because you always get these pairs of complex conjugate numbers, the expression here would always be a function with real coefficients. So what I'm trying to say is, yes, bk and alpha k can be complex, but because they would always, if there are some complex numbers, then there will be always a complex conjugate number as well. So when I look at the sum of these two, I will get a real function. So you will not get complex. If you get in the end that g of t is a complex function, you made a mistake. You made a mistake. So that's proved in the next slide. So if you look at pairs of b and alpha k's with their complex conjugates, then you can carry out a calculation by saying, well, now bk times e to alpha kt plus bk conjugate times e to alpha k conjugate t is in the end a function that looks like this, and all of these numbers are real. So follow these steps. This is simple algebra using the representations of complex numbers in this way. So I start from this representation and just sort of follow. I really included every step in the derivation to basically say, here I have complex numbers, but because there is a sum of those, I get something that's real, right? So that's important. That's important. Any questions? All right, so what we can also say is if we have repeated poles, so in other words, if you have that some alpha 1 repeats k1 times, and then alpha L repeats kl times, the formula for residuals changes slightly, and it's given in the next slide. So you just need to apply this formula instead of the previous formula I gave you. But the story is pretty much the same. So you will then get terms that look like this. So the simplest expression for G of S is given here. We now know that these B's have double indices. They are double indices because one of the indices corresponds to the distinct pole, and then the second index talks about, well, multiple residuals corresponding to the same pole. Right? Because you will have many terms corresponding to the same pole in this expansion. So the formulas for these B's are given here. So that's basically like the most general partial fractional expansion that you can find. And again, you know, you just need to solve a few examples to get a hang of it. But the story is pretty much the same as what we had before. You just have to be careful in applying these formulas. By the way, students often some students do, when I say students often do, I mean on average, looking at the population, when I look at the exams, you make mistakes in partial fractional expansions. But you know, it's easy to check. You know, once you got that, well, you can add these things up, and what you need to get in the end is this. So you can easily check. Once you got this, you can easily check by sort of representing it, finding least common, you know, denominator, whatever. You know, it's like you just sort of manipulate these guys, you know, so that you first get this sort of representation, and then when you multiply out all of these guys, you get this representation. So what I'm suggesting is, whenever you find partial fractional expansion, multiply, you know, add it together, and you have to get back what you started from. So it's a check. And this check typically doesn't take much time, but students often don't do it, right? So my advice is do it. You would lose a few points. Typically when we mark, we want to see that the steps are correct, that the reasoning is correct. Algebraic errors are not big deal, right? But you do lose some points. So if you're aiming for a really high mark, obviously if it's not a correct answer, you can't get a perfect mark. But we do mark down more conceptual mistakes. Right? Conceptual mistakes are really marked down, more than algebraic ones. All right. In MATLAB, you can easily go from transfer function representation like this. So basically, if you define numerator and denominator in your transfer function, so numerator, what is given there? There are coefficients in the top polynomial, right? And denominator here, there are coefficients in the bottom polynomial, right? So note that the top polynomial has coefficients 2, 5, so 2 times s to the power 3, 5, s squared, etc., right? So that's how you define polynomials. And then if you want to find, you know, the partial fractional expansion, you basically say, calculate the residue of this numerator denominator. Well, residues are basically these coefficients on top, right? And these are the sort of poles. K is just a constant term that is added at the end. So that's like the most general sort of situation you can have. And I mean, MATLAB does it quickly. In an exam situation, you won't have MATLAB. So I still need to sort of talk about this. And by the way, sometimes you just say, well, since I have MATLAB, I don't need to understand anything. MATLAB will do everything for me. In order to check the output of MATLAB, you need to have an understanding of the material. Because you will just trust blindly, MATLAB can become a black box that you don't understand at all. So you can't use MATLAB like that. You need to have an understanding to even interpret the results that MATLAB gives you. So that's why we still have to go through this material. All right, so what we did, we first sort of overviewed some complex numbers, then we presented Laplace transform tables, and we went through several examples, and then presented formulas for partial fractional expansion. Partial fractional expansion you will use over and over and over again. Please, please revise it. At the end of these slides, I gave you, several, like proofs to prove some of the entries in Laplace transform tables. Please go through these because it will help you understand the material. So I urge you to also go through these slides which we didn't cover. I assume you've done this already in signal systems. Signal systems is a prerequisite for this subject, right? Okay, any questions? Well, thank you very much. You were very nice to me today, so thank you very much.
Several questions. The first one is about in Laplace transform we get a regional convergence there. I want to know what's the meaning of convergence. It means that we get a finite value of points.
Well, it exists. So it just exists. So basically, if you try to sort of work with outside the region of convergence, it wouldn't exist. So
I find that for this Laplace transform, we get a region of convergence like sigma is positive, and and sigma is the real part of S, and if the S is a real number, it means that
positive real numbers. That's yeah.
And when we perform the Laplace transform, should we always check the region of convergence?
Look, typically the way you do it, you bear in mind the region of convergence, but typically questions we formulate, you can sort of swipe it under the carpet in most questions. Right?
And I have another question that. For final value theory, we must make sure that if the time is infinite, we must make sure that there's a limit exists. But if we only perform the Laplace transform from differential equations to get YS, and how could we
we'll talk about that soon so what you need to look at is that Y of S should have, poles, like in the representation that I had at the end. We had pole zeros. Well, poles should be with negative real part. Perhaps one pole at the origin is allowed, but all of them should have strictly negative real parts. And that is a check in complex Laplace domain that you can apply finally.
And a final question that in slide it means delay, but I do not understand why it means delay. And
so basically here you have time and you have tau. So basically t minus y of t minus tau, you have to look at first y of t. So y of t is basically function that looks like this maybe, but y of t minus tau is the same function shifted by minus tau in this direction.
But what's the
Sorry,
meaning of mu?
sorry, it will be different shifted in the other one. Sorry, mu is the step function also shifted by the same amount. Right. So it's a step function. It's a function that is 0 for negative argument and 1 for positive argument. So when t is greater than tau, it is 1, and when t is smaller than tau, it is 0. That's the function.